Hello everyone. In the last class, we started together in this example. So it's numerical example on three-phase transformer. So I'm gonna remind you about this example and continue discussing the topics of the three-phase transformer. So here, guys, in this example, the example says three single phase. So this is again three single phase means this is a three-phase transformer bank, which means we have three single phase transformers connected together to form a three-phase transformer. So three single phase, 50 kVA. So this is the apparent power of one phase. 50 kVA is the apparent power of one single phase transformer. So this means the three-phase connection of this transformer can support up to 3 times 50 kVA, which is 150 kVA. So this transformer can be loaded by 150 kVA. However, this doesn't mean our load is going to absorb this amount of power. It depends on how much load we are supplying from this transformer. Okay, but the capacity of the transformer is 150 kVA. And then 2300 to 30 volts. So this means the primary to secondary turns ratio or volt is 2300 to 230 volt. This is again of a single phase transformer. 60 hertz are connected to form three phase 4230 volt. So we mentioned that the 2300 to 30 is the single phase and the required three-phase transformer need to be connected to a supply of 4000 volt and a load of 230 volt. In order to do that, guys, what should be the connection? We mentioned, guys, if the volt of the three-phase is similar to the volt of the single phase, so this means the connection is delta. And if the volt is different, the connection is going to be Y. Because, you know, for Y connection, you have the line volt equals √3 times phase volt. And in delta connection, phase and line voltages are equal. So, since we have primary volt is different to the primary volt of the single phase transformer, so we expect that the primary winding is going to be Y. And the secondary volt is 230. It's similar to the secondary volt of the single phase one. So this is going to be delta connection. Then the example says the equivalent impedance of each transformer referred to low voltage is 0.012 plus J 0.016. So this is now the impedance, resistance, and reactance of our windings, the winding resistance and the leakage reactance of the transformer for both of transformer sides, but refer to the low voltage side. Low voltage side here, guys, is the secondary side. So here we can say this is Z equivalent to or Z equivalent low. Either subscriptions are fine. So this is the secondary or refer to secondary transformer impedance. Then he mentioned here that a three-phase transformer supplies a three-phase 120 kVA 230 volt 0.8 power factor lag. So this is our load. As we mentioned in the beginning, he said 50 kVA, and we concluded that transformer can supply up to 150 kVA, which is 3 times the single phase capacity. However, the load here is not a condition to be the same as rated value or the full capacity. The load here is less than that. It's 120 kVA. So this is our apparent power that we are going to analyze our transformer. First thing, draw the schematic, and we discussed the schematic that time. Second thing here is determine the transformer winding currents. So we calculated the current. C, determine the primary voltage line to line. We also calculated the primary voltage line to line. And D, we didn't solve part D yet. So D, determine the voltage regulation. If you would like to determine the voltage regulation, so you know, guys, the voltage regulation is representing the drop across the transformer related to the rated volt. So what we need to do is we need to get V2 prime and V1 in order to do that, or V1, and we have already V2 prime. So this is part D. We already calculated V1 in the previous class. So V1 is the line-to-line value, which is 4039.8, and V2 prime is nothing but the 2300. But take care that 2300 is phase volt. This is phase volt, and this is line volt. We cannot subtract line from line. So what we should do, you can use the line or the phase. So you have the line, which is 4000, or you can use the phase values. Here in the textbook, he considered the phase values. So we already calculated the phase value. So this is V1. I'm going to say this is V phase. So we use the V phase value here, minus the phase value, divide the phase value of the transformer V2 prime, and we got the volt regulation. Or you can say volt regulation percent equals in terms of line value. So this is going to be 4039.8 minus 4000 divide 4000. From where we got the 4000, 4000 is the line to line of the 2300. If you remember, here it's mentioned that the primary volt is 4000, and this is nothing but V2 prime line value. So both solutions are fine, and since this is percent, so we should multiply this times 100, and it would be in percent. So this is, guys, how can we calculate the volt regulation in three-phase transformer. So you can use the phase value or line value, no problem with that. But again, if you use phase value, so you should use phase value for both V1 and V2 prime. And if you are going to use line value, so use the line values for V2 and V1, V2 prime and V1. Okay, so the relation again, guys, I'm going to write down the relation again here. So volt regulation is V1 minus V2 prime divide V2 prime. So this is the relation of the volt regulation. Here, guys, in this transformer, this question didn't ask to calculate the efficiency. I'm going to ask you now part E, and this is going to be quick assignments. Determine the transformer efficiency at the same loading condition in actually it's in all the questions, so it's not in a single part. So just determine the transformer efficiency at this loading condition. So please solve this part of the question and turn it in by Friday, by this Friday. So this is again, this is quick assignments. Okay. Now, let's see another numerical problem here. So this question says a three-phase 230 volt 27 kVA 0.9 power factor lagging load. So this is a three-phase load. Okay, so these specifications here, these specifications are for a load. So he says this load is supplied by three 10 kVA 1330 over 230 volt 60 hertz transformers. So again, this is three single phase transformers, and the ratings and the voltages here are for the single phase one. So we have three transformers. Every transformer is 10 kVA, and this is the volt of every single phase. 100% guys, this cannot be a three phase because as you can see here, the load is 27 kVA and the transformer is only 10 kVA. So we cannot supply a load of 27 kVA from a transformer of 10 kVA. So this is the rating of a single phase transformer. Okay, so we have three of these three of these single phase transformers. So he mentioned here, guys, these transformers are connected in Y delta. So the connection is going to be Y for the primary side and delta for the secondary side by means of a common three-phase feeder. So the load is connected to the transformer through a feeder whose impedance is this value per phase. So if you would like to see this part right now, we have a load here, and the load is 230 volt, and we have a feeder between the transformer and our load. And this impedance is this value right here. Then the transformers are supplied from a three-phase source through a three-phase feeder. So we have another feeder between the supply and the transformer. So here is our supply, and this is our transformer bank, and we have a feeder in between. And he gave the value of the impedance. So this is the impedance per phase of this transformer. Per phase, guys, means every phase. So for sure, we cannot have something called three-phase impedance. So three-phase impedance is nothing but three single phases. So every phase will have a certain impedance. So all of the time, the impedance is going to be per phase. So the equivalent impedance of one transformer referred to the low voltage side is this value. So again, this is the equivalent impedance, the overall impedance of the transformer, referred to low voltage side. Low voltage side, from the data given here, is the secondary side. So we can say this is Z transformer equivalent to or low, because this is referred to the low voltage side. What is needed here in this example? We need to determine the required supply voltage if the load voltage is 230. So this is our load volt as we mentioned, and we need to determine the supply volt. What would be the supply volt? So this is again a straightforward numerical example. We can just solve it like the previous example, but instead of having only the transformer here, we have also two other impedances. Impedance in the secondary side of the transformer and another impedance to the primary side of the transformer, and then connect it to the supply. Okay, so in order to solve this question, remember that you have the options to make the complete circuit analysis, either refer to the secondary side or to the primary side. It's up to you. But when you make the transformation, don't forget to use the transformer turns ratio in order to transfer the impedance in the right way. So let's see together, guys, how can we solve such a problem. So this is the solution of the textbook. We will see and analyze this solution, and if we have another idea or we can solve in another way, we will discuss it together. So the equivalent circuit of the individual transformer referred to the primary side is, so first thing is, he referred the impedance to the primary side. So this is the equivalent impedance of the transformer. And this is the turns ratio of the single phase transformer. So he referred this impedance now from the secondary or low voltage side to the high voltage side. So how can we do that? You remember, guys, V1 divide V2 equals N1 divide N2 equals turns ratio. We mentioned that if we refer something from the secondary to the primary side, so we can say V1 equals V2 times N1 divide N2. So we will multiply times turns ratio. The impedance will match the volt in terms of turns ratio, but the impedance will be multiplied times square of the turns ratio. For that, this is the secondary side, or the impedance referred to the secondary side. We will multiply this times our turns ratio square. So don't forget that, guys. Impedance will multiply times turns ratio square, but current and volt, we use only turns ratio without square. So this is going to be the ohmic value of the impedance now referred to the high voltage side. Good. But take care, this is only the transformer impedance, not the feeder impedance. Okay, nice. Then he mentioned here, guys, the three-phase system can be described as follows. He connected the transformer as Y delta transformer. Why he did the connection like that? In order to figure this out, let's go back again and see the transformer volt and the load volt. So here, guys, as you can see, the load volt, the three-phase volt, or the line-to-line volt of the three-phase load is 230. And our single-phase transformer has a rating of 230. So we mentioned that if the three-phase volt and the single-phase transformer volt are the same, the connection has to be delta connection. So we can figure out that the transformer here is delta connection. Okay, so this is the first thing. Now, this is our connection. It's delta connection here. And this is our feeder impedance, and here is our transformer, secondary side of the transformer. So this is the secondary side, and this is our load. The question is, here in this example, guys, he considered the transformer here as Y connection. If you read the question here, guys, do we have anything require the connection of the primary to be Y? If we read the example again, we don't have anything says that primary winding has to be connected as Y connection, because we don't know the supply volt. Okay, guys, we don't know the supply volt. So here in this example, you have the options to assume that the supply is delta connection. Sorry, not the supply. The primary side is delta connection or Y connection because it's not mentioned here. But if you remember, guys, we mentioned before that this transformer here is considered as medium volt, and this side is low volt. So most of the time, the primary and secondary sides of the substation transformers or distribution transformers are not common. So the primary and secondary connections are different. Sorry, guys, it's mentioned here. Sorry, it's mentioned here. So it's already mentioned. So the transformers are connected as Y delta. So the primary is Y. So this is, I didn't see that, sorry. So this is mentioned here. But if it is not mentioned, you have the option to select between Y or delta. Okay. So sorry again, guys, he mentioned here the connection is Y delta. So we can now consider the primary connection as Y. But again, if it is not mentioned, you have the option to make the connection or Y in Y or delta. But again, practically, most of transformers, we use it in substation and distribution, have different connection from primary to secondary. If you remember our discussion in the previous session, we discussed the different connections and we mentioned where you can find the different connections of three-phase transformers. So this is our Y connection, and here we have our other feeder. Now, in order to get the volt in this side, guys, we need to convert our question to a single line diagram or single phase. How can we do that? So here is this impedance again is the referred impedance of the transformer seen from this side. So this number here, Z equivalent 1, is the transformer impedance. But we still have another impedance here which is not considered yet. So let's see, guys, how the textbook here is gonna solve this part, and we will see if we have another way to transfer this impedance. So here he mentioned to convert to a single line diagram, delta connected transformer has to be converted to Y. This makes sense because if you have Y connection, a single phase of the Y connection can be considered as a single line diagram. But delta connection, no, it's not a single line, or we cannot have the single line diagram from the equivalent delta. We have to convert delta to Y. So therefore, the three-phase turns ratio is A prime equals √3 times the single phase primary volt divide the secondary volt. So if you do that, √3 times 1330 divided 230, it would be 10. So the line volt is √3 times 1330 is 2300. So this is going to be the three-phase turns ratio, and we call it A prime. So what we can do now, we can start making our calculation and using the three-phase equivalent. So this is the delta or the line volt. Here is our feeder, and this is the equivalent Y connection of our transformer. So if this is 230 volts, so we can use the current flowing here and get our equivalent volt here, and then use our turns ratio. So again, A prime is A times Vx divide √3, because if you have here a Y connection, if the volt here, if this is the the phase volt, which is line divided root 3. And this is the phase volt here, multiplied times Turner's ratio. So if you divide this volt, divide that volt, so AVX divide Vx divide root 3, it will provide you with the value of A prime, which is our Turner's ratio. So this is the right representation in case of equivalent Y connection for the secondary side. So we can start our calculation now from the load side. So we can say I2, which is the current flowing to our load here. So this is I2. It's equals to S divide V line to line divide root 3. So S is the three-phase power of our load, which is 27 kVA, divide 230, which is the line volt, times root 3, Y times root 3, because you know that the three-phase power equals root 3 times V line times I line. So this is a relation of our apparent power. So getting I, so the I would be S divided root 3 V line. So this is the current in the secondary side right here. So this is I2, this is VL, which is 230 volt, okay? But if we convert this to a single phase, so this would be line to neutral, so this would be 230 divided root 3. So this is our line current. For the Y connection, you know that line current is similar to phase current. So what we can do now, we can start solving the single line diagram, because now we converted the delta to Y. So simply we can have the calculated current here, which is going to flow in our transformer and will be transferred to the primary side using our Turner's ratio of the three-phase. And then we have the feeder impedance here. We have everything in the primary side, so we can do our calculations based on that. So let's firstly refer the current to the primary side. So I2 divide A prime. A prime, you know, it's the three-phase transformer Turner's ratio, 10. So we can say 67.78 divide 10. So this is a primary current right now. And we can start making our calculations now. So for the Y connection, again, let's go back here. This is going to be the volt of line to neutral, which is AVX. And you remember that the single phase transformer is 1330 volts. So single phase transformer is equivalent to the phase volt of our Y connection. So when we convert this to a single phase, so this is 230 divided root 3, it would be going to the other side as the volt. So if you multiply this times 10, it would be 2300 divided root 3, which is 1330 volts. So the transferred volt is 1330. So we can say V1 is 1330 volts. So, sorry, V2 prime is 1330 volts. So we can say here V2 prime plus I2 prime times this feeder impedance. But take care, we have to refer this to the primary side. Z equivalent 1, we already calculated Z equivalent 1. And Z feeder 2, it's already in the primary side. So if we say now V1, it would be 1330 plus the current times the summation of these impedances. But we still didn't get the feeder impedance referred to the primary side. So 1330 is our reference volt at angle 0. And this is the current. The angle of this current is going to be the same angle of the power factor and minus sign because it's lagging. So minus cosine inverse 0.9 times summation of our impedances. Let's see, guys, the impedances again. So 0.8 plus J5, I do believe this was the feeder impedance. Let's go back here. So 0.8 plus J5, this is the second feeder impedance, this one. We already transferred the Z equivalent to the primary side. Now, this is the feeder impedance, which is physically on the secondary side of the transformer. So we need to get the referred one of this impedance to the primary side. So we will use the Turner's ratio. So here, guys, you will find that this is our feeder, Z feeder 1 impedance, and we need to refer this to the primary side, so we will multiply times Turner's ratio square. So Z feeder 1 equals, sorry, Z feeder 1 referred to primary equals Z feeder 1 times Turner's ratio square. Now you will get the single phase or the phase value of the supply volt referred to the primary side. So this is the volt now 1407. For sure, guys, when we solve three-phase transformer and we ask to calculate the volt, we should provide the coupling volt, and the coupling volt is line to line. Since the primary winding is Y connection, so you know that V1 line to line would be V phase times √3. So this would be the primary side volt. Okay, guys. So I think the textbook solution is the very simple solution to be considered. So I don't have another way or easier way to solve this question. So this is going to be the best way to solve this example like that. Again, let me summarize. How did we solve this question? So firstly, drawing this schematic will help you to figure out what is in primary side, what is in secondary side. So this is very important. Mention the values, then start drawing the connection, the three-phase connection of your transformer and other network, and then draw the converted connection in order to provide the voltages and currents. So this will help you to identify the different values of phase voltages and currents. Okay. Again, here we use the three single phase transformer connection and convert everything to the Y so we can get the single line diagram on the Y connection. So this is the way, guys, how can we solve this question. Okay. We have some notes here. For the last problem, you should be able to calculate the input power factor, the losses of any feeder, the voltage drop across the feeders, and the transformer losses. So this is, guys, since you already calculated the currents, you can make any kind of evaluation. For instance, how can I get the input power factor? I already got the current with angle, and I have now, or I calculated the volt. So what I can say, the power factor of the supply or the input power factor of our transformer is going to be cosine theta V1 minus theta I2 prime. So here in the question, this is theta V1, so I can say theta V1 equals 3 degrees. And theta I is already calculated from the power factor. But take care, this is theta V1 as V phase. Okay, this is theta V1 as V phase. Okay, now the question, can we calculate the power factor from theta v phase or theta v line? Yes, you are right. All of the time, power factor is cosine theta v phase minus theta I phase. There is nothing called cosine theta v line minus theta I phase. This is nothing or means nothing. It's not the angle of the power factor. Okay, guys, cannot calculate the power factor from the phase shift between the line volta and phase current. All of the time, for balanced three-phase loads, the power factor angle is cosine theta v phase minus theta I phase. Okay, guys, so this is one of the basics you have to understand. All of the time, the power factor, let me write this note here. So this is here phase all of the time. Because again, power factor equals cosine theta v phase minus theta I phase. Because the impedance is nothing but the phase. Okay? Nice. So this is how to calculate the input power factor. If you'd like to calculate the feeder losses for any feeder, primary or secondary, you know feeder loss is going to be I squared times R. But don't forget this is three-phase system, so you have to multiply times 3. So for instance here, this is, guys, this is per phase, so don't forget to multiply times 3. For instance, if you would like to get feeder 1, let's see feeder 1 right here. Okay, this is feeder 1. If I would like to get the loss across feeder 1, so I can say P loss feeder 1 equals 3 times I2 prime square times R feeder 1 prime. So R feeder 1 prime is this value times 10 square. Okay, so this is the way how can I get the loss here. This is the way. Another way is you already calculated the real current flowing in the line here, which is 76. So you can use this value. So 3 times this value square times the resistance without transformation. So this is still possible. Okay, and all will provide you with the same value. If you would like to calculate the other feeder loss, so I can say here P loss feeder 2 equals 3 times I2 prime square, the same current, times R feeder 1. Sorry, this is feeder 2. R feeder 2. Okay, I don't need to make any transformation for feeder 2 because it's already on the primary side of the transform. So this represents the loss across this transmission line. If you'd like to calculate the voltage drop across any feeder, so it's nothing but current times impedance. Okay. The transformer copper loss, you know that in transformer, guys, we have copper and core losses. Okay, so the transformer copper loss can be calculated as I squared times R. So you have the R equivalent refer to primary side, and you have I2 prime. So we can say, again, this is for per phase value. So I can say P copper of the transformer equals 3 times I2 prime square times R equivalent 1. So this would provide the copper loss of the three-phase transformer. Okay, nice. Here, guys, if you remember that we have core losses, and we use this term in the open circuit and short circuit test and parameter identification, so we can get the core loss from the open circuit test. If you can see here in this question, we don't have this core loss. It's not mentioned, which means it's neglected here in this example. However, if you have a complete data or exact model, so there would be another branch in parallel, which is the core branch, and you would have some core loss across this branch. But again, here in this numerical example, for simplicity, we did not consider this type of losses. Okay. Now, let's fly to another idea here, guys, which is the open delta connection of our transform. We mentioned before that we have 4 well-known connections for the transformers. These connections are YY, Y delta, delta Y, and delta delta transformers. And we mentioned that we have some other special connections. So special connections like zigzag connection, like open ends connection, and one of the special connections also, guys, called open delta connection or V connection. So what is V or open delta connection? Simply, if you have a 3 single phase transformers and you removed one of these transformers, so you would have only 2 transformers available. These 2 transformers will represent 2 phases in shape V, like that. Can you see here? We remove this transformer. So this is the primary of the transformer and this is the secondary of the transformer. So if we remove this transformer, we would have now like V connection. And this is called open delta connection. The advantage of this connection, guys, is you can use this connection to make maintenance for your transformer. But you will lose around 42% of your load of the rated capacity of your transformer. So the remainder power would be only 58%. Okay. Why? We can see this in short derivation in the coming slides. So this configuration, guys, is called V connection or open delta connection. It may be employed in emergency situation when one transformer must be removed for repair and continuity of service is required. So this is one of the advantages of using the open delta connection. So here, guys, for instance, here we have a simplification of Y connection. So if you have here, this is VAB primary, primary VAB, VBC, and VCA. So these are the 3 line voltages, represent the line to line of the primary side, and the equivalent line to line for the secondary sides are here as well, VAB, VBC, and VCA. For inductive loads, guys, the current IA, IB, and IC will be lagging corresponding voltages VAN, VBN, and VCN by the load phase of angle phi. So if you assume that you have inductive loads and this is VAN, so we would have IA here lagging this load by angle phi. And here this is the phase shift between the equivalent phase in case of Y connection. Okay, and this is the line volt. The transformer winding AB and BC delivers power. These powers are power AB and power BC. So we can consider these powers, guys, like the 2-phase or 2 wattmeter method that we had discussed before. So VAB times IA times cosine theta plus 30, okay, and theta minus 30. So this would represent the power of the 2 phases. So if you add these 2 powers together, and calculate the power of your two phases. So this would provide root 3 V phase I phase cosine phi. So this is the power of just two phases, which is PV or open delta. If you compare this power to the regular three-phase power of the delta connection, you will find that there is a ratio of root 3. So if you divide P open delta, divide P delta, you would have 1 divide root 3, which is almost 58%. So this means you can provide power of 58% if you lose one of the transformers, one of the three-phase transformers. Okay, so you still can provide power to your load, but with reduced capacity. So you can reduce your load to 58% of the capacity of the transformer, and then you can open one winding of the transformers. Take care, guys, that most of the time we don't have rated load for the transformer. And we shouldn't design our transformer to work at rated all of the time, because the efficiency at rated is going to be a bit less than the maximum efficiency. So this is one thing. And another thing is, all of the time we should consider like a safety factor for our loading, but we have something else called load factor, so it can compensate this safety factor. However, experience-wise, guys, you may not find transformers in substations with rated volt most of the time. So having reduced load on transformer is not a big deal. It's easy. So it's easy to reduce the load to 58% and remove one of the phases for maintenance, or if you have any kind of fault, so you can remove this phase and start make your fix your problems, solve your issues, and then reconnect this single phase transformer again. Okay, so this is the benefit of having open delta transformer in our networks. So again, guys, this is now a comparison. If you have the power, so it could be 58% as we just mentioned. So we will stop at this point here, and in the next session, guys, we will discuss the three-phase unit transformer. So we discussed now the three-phase transformer as three single phases, but in the next session, we will discuss the three-phase transformer as a single unit, and we will have more discussions about the formers and transformer core and transformer cooling. Thank you so much, and see you in the next session. Have a good day.